Now, let's see. Today we are going to go on to talk about protein structures, primary and secondary structure. But before we do that, I wanted to go ahead and um, just a second. I'm sorry, everyone. So, at any rate, sorry about that. So, what I wanted to talk to you guys about today, and before we really get moving, is I wanted to go ahead and work through drawing a dipeptide and using kind of a simplistic model for doing as much. Hopefully, this will make it a little bit easier to kind of process the information. And so, what I'm going to do is I'm going to close this file. And I'm going to save that as going to open up 1%. And this is protein structure, primary and secondary structure. But also, I'm going to pull back some of the peptide stuff from last time. So, the important things that you need to know about drawing a peptide and being able to kind of understand what's being displayed in a peptide is all related to the charge and the pKa and calculating the pi. So last time in class, we were talking about calculating a pi and drawing and visualizing a peptide. And we're going to continue on with that. But right now, my mouse is being super sensitive and double clicking for everything. Um, so here we go. So I want to share with you guys this slide right here. And what I want to know, and one of the things is that you do not have to, and I've said this before, I'll say it again, you do not have to know these PKs by heart. These are all the PKs that I will provide to you. Okay. Yeah, great. Um, yes, but we're still working out I got a private message about missing last class. Um, everyone, just for the next few class periods, everyone's going to get complete credit for participation, just because I don't want anything that's like a persistent technological issue to kind of throw you off. And so here we go. So here we go. I got that all set up. Okay, so this slide right here is a really good one. And what I would do is, oh, not that. I would go ahead and just sort of temporarily think these two tables, they're not so much that you have to commit those numbers to memory, but they are important numbers for you to kind of make sense of. Now, one of the things that I've said before and I will say again is that every single amino acid has two major functional groups. One of them is on the N termini, where it is an amino group, and that group can be protonated or deprotonated. As it's shown right here, it has a charge of +1. Now that same group as this depiction, it is protonated. Can it be deprotonated? Absolutely. And when it is deprotonated, it looks a little bit like this. The nitrogen has two protons or two hydrogens going to it, and it has a lone pair of electrons. And whenever it looks like that, it has no charge whatsoever. The C termini of every amino acid, I'm going to go ahead and erase my alpha carbon there. The C termini looks like this. When it is protonated, it has an OH, a carboxylic acid or a carboxyl functional group, and it has no charge whatsoever. When it's deprotonated, it looks like this and has a -1 charge. Okay, so one thing that I want to make clear is that this combination, so the N termini and the C termini, you will never see the C termini protonated, so this, and the N termini deprotonated. And the reason for that is the pKa of your N termini, and I'll jump back a slide to show you. If you look at all of these N termini right here and here, they're closer to 9. So if the pH is below 9, then it's going to be a group that's protonated. And so this is, I'm going to call this like 9.XX just as a filler. The C termini, this has a pKa of about 2.XX. Now, what I'm getting at is this group right here, the N termini, will be deprotonated as it's shown here, deprotonated when the pH is greater than 9.XX, 9.5, 10.25, whatever. Well, if your solution pH is greater than 9, well, then this group right here is going to be deprotonated. Okay, that's one of the important things that you always have to kind of wrap your mind around and think about when you're visualizing a structure or when you're looking at a structure. Okay, what's the realistic pK or the pH based on these pKa's? Now, one of the exercises that I will ask you to do is I will ask you to tell me the charge of a molecule, and I'll ask you to tell me the pi. And am I recording? Yes, I am recording. The pi of a molecule. Now we're going to start with a dipeptide. And the dipeptide that I'm going to draw, or I'm going to ask you to know is, let's go with, I like to use names. I also like to use kind of acronyms or something like that. So let's go with a neighboring state, LA, Louisiana. 2-letter sequence for Louisiana. This is a dipeptide made up of leucine and alanine. Both of these amino acids are diprotic amino acids. I'm going to jump back so that I can grab those pKa's. Leucine, 9.74 and 2.33. I'm going to jump back over here. L and A. N and C, 9.74 and 2.33. Now I'm going to go back to look at alanine. Alanine is 9.87 and 2.35. Very similar. All these molecules are pretty similar to one another. 9.87 and 2.35. Private message question, a little random, but will we ever deal with a beta amino acid? No, I don't believe that you will in this class or in metabolism. Yeah, so no, we will not. Your beta amino acids, they do exist. They can exist. They are relevant to, I believe plant hormones they're used in the synthesis of some plant hormones. But we're not too interested in beta amino acids. But it's good to know that they do exist. So anyway, okay, so we've got leucine and alanine. Now, what I always like to do is I like to draw out my peptide without actually drawing it. And what I'm going to do is I'm going to put this nice little box around it. And this is my way of visualizing my dipeptide. This is my N termini, and this is my C termini. Now, I'm going to go ahead and fill in any charges whenever this molecule is at a pH of 1. At a pH of 1, I know that my N termini is going to be protonated, and I know that because a pKa of 9.74, well, 1 is below 9.74. So that N termini is going to have a positive charge. I'm going to jump back. So the N termini of this peptide looks like this right here. Now, to avoid some confusion, I'm going to go ahead and erase lots of this just so nobody's looking at it and like, oh, what did he mean by that? What's with the circles? Okay, so this is what the N termini of this LA looks like. Okay, I've got my positive charge to indicate that. Now, next up is my R group for leucine. Well, leucine has a non-ionizable side chain. It's a non-polar amino acid. So the R group pK or charge is going to be zero. And it's actually going to be zero across the entire pH range. There's no pH at which the R group of leucine is going to be charged. Now, the next thing is my 2.33. And this is kind of a tricky point. This is the C termini of leucine. And I want to do this just so that we're all on the same page. I have a peptide bond that links the C termini of leucine to the N termini of alanine. That is within a peptide bond. And because it's within a peptide bond and a hydrolysis reaction has taken place, that group is not ionizable. Neither of those groups are ionizable. So I'm actually going to omit those altogether. So I don't have a charge resulting from the N termini or C termini the N termini of alanine or the C termini of leucine. So that brings me to my R group for alanine, which, again, it's a non-ionizable side chain, so that's going to have a charge of zero. My last group is my C termini of alanine. Alanine, at a pH of 1, the C termini is going to have no charge whatsoever. It is going to look like this right here. So when my molecule is fully protonated, this is what my N termini looks like, and this is what my C termini looks like. Those come together to give me a charge of +1. I have a total of 2 pKa's. So what I'm going to do is I'm going to erase pH of 1 because I was just using that to sort of establish, hey, this is what I'm drawing it at. I'm going to give myself a number line. I'm going to say +1. Then I'm going to go to 0 because when one of these groups gets deprotonated, which is going to be the C termini as I'm adjusting my pH upward, this will take on a negative charge and look like this right here now. Now all of a sudden I have a -1 charge on my C termini. My N termini has a +1 charge. That would add up to have a 0 charge whatsoever, or completely. Now, so that means that group, that pKa has kind of been dealt with. I'm going to write 2.35 above my line that goes from +1 to 0. Now, I have another pKa, 9.74. And when my pH is above that 9.74, the predominant or most common form of my molecule will have an overall charge of -1, which means that my N termini no longer looks like this right here, but now looks like this. So at a super high pH, my molecule has this combination of N termini and C termini ion forms. So those two, the -1 and the 0, will combine to equal -1. Okay, so that's a quick way to do that. And so we looked at those different charges. This molecule, La, can have a possible charge of +1, 0, or -1. It will not have a charge of -2. It will not have a charge of +3. This is the range of all the possible charges at every single possible pH. So in terms of charges, those are the possible charges that are there. Now, with that said, the next thing is, what about our pI? Well, our pI is the pH where 100% of the molecule has a 0 overall charge. Now, that is a net charge of 0. So negative charges add up to, there are an equal number of negative charges and positive charges, so they cancel one another out. Now, to arrive at that, we take our two PI or two pKa's, 2.35 plus 9.74, and divide that by 2. So I'll plug this in. 2.35 plus 9.74, and that gets me 12.09 divided by 2. And so we get 6.045 or 6.5, 6.05. Okay. Now, that is a dipeptide. That dipeptide has nothing but nonpolar R groups. It gets a little bit hairier and a little bit more complicated whenever you're adding something like an ionizable side chain to it. So I'm going to move ahead and we're going to do another. And an important thing is we didn't have to draw this molecule, and you don't have to draw this molecule, but we did have to know some information about this molecule, specifically its pKa values that were displayed and how to negotiate and navigate those. So now let's go ahead and let's go with RCD. RCD. That is arginine, cysteine, and aspartic acid. Now, I've got all of these pKa values. I'm going to make that same chart that I had a moment ago. I've got my, how were you able to get LA, or was it a random code? This would be a problem that I would provide for you. So LA is just reflected in, hey, given this peptide, what is, or what are the possible charges and what's the PI, which is what we're going to do right here. Okay, sorry, I missed a question. Are all structures for amino acids provided anywhere? As I couldn't find some. Uh, okay, so all of the amino acids are provided in the slide decks that I've posted on Canvas. So lysine, for instance, in fact, on this slide deck, if we go back to um, lysine, arginine, and histidine, I believe are on the first day slide deck. So they are all out there. And if you want, I can take those images. I'll add this on my things to do. AA structures. I'll put them in a good reference file so that you don't have to like sift through and sort through different things. So I will add that to your Canvas site and I'll send an announcement out about them. Okay. Thank you guys for the questions. I'm a bit confused how you choose which numbers to use and which ones you don't use. Okay, we're going to go through this example so that you can kind of dissect those and look at them again. Okay, so N termini, C termini, and R group. N corresponds to the N termini of my amino acid, C to the C termini of my amino acid, and R to my R group of an amino acid. So what I'm going to do is go with now on our x-axis here, I'll write the 3-letter codes. Hopefully that will help out a little bit. ARG, CYS, and ASP. Could I also include the PKs in the amino acid doc? Sure thing. That will be good. So then you guys have those as like, these are the numbers you're going to see on your exams. So that will be a good reference point. Okay. So this is my table where what I'm going to do is I'm going to pull these numbers right here that are relevant to the problem that I'm about to do. So the first numbers that I'm going to get, and I'm doing them a little bit out of order. I'm doing them in this order right here. The first number is for CYS, 10.25, 10.25. Okay. Next up is cysteine's C terminal pKa value is 2.05. And what might be helpful for you guys is as I'm doing this, get a piece of paper out and work on it yourself as well so that you're working alongside me. So we're filling in this table. My R group for cysteine is has a pKa of 8.00. So I'm going to put that in there. The only reason I put cysteine Info first is because that was the first on the table on that previous slide. Now I'm going to go to ARG, arginine, 9.04. So now I'm right here, 9.04, 9.04. Then my C termini of arginine is 2.01. And then last but not least, what is the pKa of my R group for arginine? 12.48. Okay. All right. Last but not least is aspartic acid or ASP. Sometimes you might see this written as aspartate or have heard aspartate. Aspartate and aspartic acid, the same molecule, one's in its ion form. The single letter code for that is the capital letter D, 9.82, 2.10. I'm going to see if I can remember two numbers. 9.82, 2.10. I did it. And then last but not least is a 3.86. 3.86. Okay. Can you give me a one in the chat if you're good? And of course, whenever I say, can you give me a one or a zero, you don't have to participate. Just trying to get a sense of who is participating and are you good? Okay. Now what I'm going to do is I'm going to look at my group or my molecule. Okay. So what I want to do is go group by group. So if there's only two letters, it means we have a N termini and C termini. But if there are three letters, we have an NC and an R. It's a great question, but not quite. So if you look back at this example, this was a dipeptide consisting of leucine and alanine. Leucine is a non-polar amino acid. And I'm going to go back a couple of slides to show you guys this. Leucine, I have 9.74 and 2.33 for that specific amino acid. So I'm just going amino acid by amino acid and asking myself, what about these functional groups? Now, I hope that whenever I'm showing you arginine, cysteine, and aspartic acid, this tripeptide, I'm going to show you the backbone. So this right here is just a super simple model that I like to use. And I'm going to show you the functional groups and go from there. So since this is three amino acids, I know that each amino acid has the following backbone, NCC. Can you give me a one in the chat if you follow that part? Okay. Then this right here, going from this C, goes to NCC. Can you give me a two in the chat if you follow that? Okay. And then NCC. Can you give me a five in the chat if you follow that? Okay. So that is the backbone for my tripeptide here. If you're looking at this and what I want you to recognize here is there's two bonds that are really important. And those two bonds I'm going to highlight in green. Could anyone add to the chat, what is the name of those bonds? They are covalent bonds. They are peptide bonds. Great. Now what I'm going to do is I'm going to show you a single amino acid's backbone. Looks like this, NCC. And heck, there we go. There's the C termini of a single amino acid at a, I'll say a neutral pH. Could you give me an A in the chat if you follow that, a Z in the chat if you say, what on earth are you talking about? Okay, wonderful. Now, an important thing about this is, and if there's something where you're like, I have no clue what you're talking about, you could send me a private message just to shift my direction a little bit. So we've got our C termini. Would you give me R in the chat if you agree that this carbon is this carbon. Okay, great. Now, in a peptide bond, we have no charge. If you look at this as our example of a peptide bond, the atoms that make up this peptide bond are the carbon and the nitrogen. Then we've got additional atoms of that oxygen and this hydrogen right here. Now, where I'm drawing a circle, or where I just drew a circle, that gives me, or what I'm looking at there is the C termini of arginine, so this functional group, and the N termini of cysteine, this pKa's functional group. Can you give me a 1 in the chat if you follow that, a 2 if you did not? Okay. Now, an important point for you to recognize within this right here is this is this is the result of N termini of one amino acid that looks like this reacting with the C termini of another amino acid. So these two reactants, or these two functional groups, come together to make that right there. Can you give me a 1 in the chat if you say, oh, okay, I follow that? A 2 if you did not. So the peptide bond that I've got a circle with a star by, that's the product of the N termini and C termini of two amino acids. Now, when those two things come together, one of the things that comes off of that is H2O. This is a condensation reaction. Now, when that condensation reaction takes place and we get this peptide bond that results, what that means is that this, or the C termini, which I'm circling right now, is no longer an independent carboxyl group. It's not an ionizable group. So that's why we get rid of the 2.01. That is also why we get rid of the 10.25. Because this peptide bond, this whole thing right here, is not ionizable. That group will not, will weather major pH changes. Can you give me a 1 in the chat if you say, okay, I understand why we drop the 2.01 and the 10.25? Okay. Now, can you add to the chat what other pKa's, based on this same principle, what other pKa's are we going to drop? Type those numbers in. 8.00, 9.82. I got a private message that says, can you please explain how again? So what's happening is when we make a peptide, this molecule right here, the way that we're making that is by a condensation reaction from the C termini of one amino acid and the C termini of another amino acid. Those two things come together, release H2O, and they release H2O and give us a peptide bond. Okay, it looks like we're listening to a little bit too much Ozzy Osbourne because we're going off the rails on the crazy train. Okay, we don't need the 8.0 and the 9.82. Oh, shoot. I was going off the rails on the crazy train. The 2.05, the C termini of cysteine, which is this right here, and the N termini of aspartate are last amino acids. So 2.05 and 9.82. Those are the two that we're getting rid of. Can you give me a T for thumbs up in the chat if you follow omitting all those pKa values? Great. Okay, so now what I can do is I can look at some of my other pKa values. I've omitted those, and what I do need to, okay, I'm going to go ahead and draw my other There we go. Okay, done, 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 done. So wherever the peptide bonds are joined is the ones we get rid of. Yes, those are the ones that we omit. You're absolutely right. Okay, so we've omitted those, and we omitted those because those are a part of a peptide bond. We had a condensation reaction that took place between the C termini of one amino acid and the N termini of a next amino acid. All right. So now what I want to do is I want to go ahead and say, all right, well, if we're drawing this molecule at a pH of 1, can you give me a 1 in the chat if you follow? We're drawing it where it's fully protonated. Okay. Now, what I'm going to do is I'm going to use blue to circle the N termini of arginine. That is going to be positively charged because when my pH is 1, 1 is below 9.04, and that group is essentially that right there. So the N termini of my peptide looks like this right here. Now, my R group for arginine, 12.48. This is my alpha carbon. The arginine R group, arginine is a positively charged or a polar positive amino acid. That group is going to be positively charged. Cysteine. Cysteine is an amino acid that, if you remember cysteine structure, does anyone remember the functional group on the R group of cysteine? Cysteine is one of two amino acids with sulfur in the side chain. It's a thiol. So a thiol, when a thiol is protonated, it looks a little bit like this. Does this molecule have a charge when it's protonated? Nope. So that is going to be 0. No charge for that. It's protonated, so we do have to consider its ionization state. Aspartic acid, the C termini is 2.10, and the R group is 3.86. Aspartic acid is a carboxylic acid, so when it's protonated, it has no charge whatsoever. So that's going to be 0. And then last but not least is the C termini of our tripeptide, which is a carboxylic acid, which is going to have a 0 charge. So now, can you give me a Y in the chat if you followed what we've done in terms of assigning numbers based on different pKa values? And an N if you do not follow. And if you do not follow, I'm glad to meet and we can talk about this and we can go through some more examples. Now, what I want to do is I want to count out my pKa values, the total number of values that I've got. I've got 9.04, 12.48, 8.0, 2.1, 3.86. Did everyone follow that? You got 5 pKa values. So, perfect. The most positively charged that this molecule can be, can you add it to the chat, the extreme positive of this molecule? +2. This molecule could never be +3. It's going to be +2. Now, what I'm going to do is for each one of the 5 pKa values, I'm going to draw an arrow. 1. Whenever I deprotonate a group, it's going to go from +2 to +1. So for the number line, we only consider ionizable groups and do not consider the nonpolar R groups. 100% correct, because nonpolar R groups are not ionizable. So we've got a total of 5 arrows that we're going to draw. -1. So I've got 4 drawn now, -2, and a 5th one gets us to -3. So our possible charges for this molecule range from +2 all the way to -3. Okay. So this molecule could not be +3. It could not be -4. It has a range from +2 all the way to -3. Now, what I need to do with this is I need to take my pKa values and I want to order them from lowest to highest. Why do I want to do that? Well, the reason I want to do that is because at the lowest possible pH, my molecule will have a charge of +2. So as I increase my pH, it will become less positively charged and more negatively charged. So now I'm going to say +2 to 2.10. 2.10, my next pKa value. I'm just listing them in order from lowest to highest above my arrows. 2.10, 3.86 is the next lowest. The next lowest is 8.00. The next lowest is 9.04. The next lowest is 12.48. Okay, so those are my possible pKa values. Those are the values that I'm interested in when it comes to my charges. Now, based on this, I look at all these numbers, and in order to calculate the pi of my molecule, what I'm going to do is I'm going to take the two pKa values that are on each side of my molecule with a zero charge. So that means 3.86 and 8.00. 3.86 plus 8 equals 11.86. I'm going to divide that by 2, and that will give me 5.93. Okay, now at a pH of 5.93, 100% of my molecule will have a net charge of 0. Now, I'm going to write that statement out. At a pH of 5.93, 100% of my molecule of this peptide, I'll say this peptide, will have a net charge of 0. Now, applying that information, and I'll say that one more time and then I'm going to be silent so you can think about it, at a pH. So if I got this molecule and put it in a solution, and the solution's pH was exactly 5.93, 100% of that molecule, every single copy of that molecule, will have a net charge of 0. A net charge. So however many negatively charged groups and however many positively charged groups there are on this molecule, they will cancel one another out. Does that mean it doesn't have any charges? Nope. That just means the number of positive charges and negative charges are equal to one another. Okay. Now, I posted a couple of videos on Thursday from my YouTube channel where I work through calculating charges and PIs of individual amino acids and of peptides. We've got this recording, or we will have this recording. We've also got Thursday's recording where we work through the same sort of thing. If you need additional help, I have no problem taking time to do that. I've got office hours tomorrow at 11. I've got office hours Thursday at 11. If there's a time other than that that you'd prefer to meet, please email me and we can set up a time. This is an essential and necessary skill, and it is something that is important for kind of visualizing and conceptualizing how amino acids change because they are taking or they are in solution, and how they change is very important for how a protein behaves. Now, I'm sorry, I don't mean to waste your time. This is a long explanation. How do you determine the potential charges of +2, +1, 0, -1, -2, -3? If the explanation is long, no worries. I'll rewatch this. I'm fine to answer that question. The way that I determined this was I went through each of the individual amino acids, and I know what those different groups look like. For example, the N-termini and C-termini of these amino acids. I said, all right, well, the N-termini at the lowest possible pH looks like this. At the lowest possible pH, the C termini looks like this. Okay. What about my individual R groups? Well, here what we have is cysteine is displayed here. Cysteine has a thiol functional group. That thiol functional group is circled right here. It's got a yellow sulfur, and that thiol, when it's at its lowest possible pH, has a zero charge. But as the pH changes, that group will go from a charge of zero to a charge of -1. So what we're doing here is we're synthesizing this molecule. A rough drawing of it looks like this. And then we're saying, how does this molecule's ionization state change as pH changes? This molecule that I've got circled in green, I threw that into a solution. The solution initially had a pH of 1. So what was that molecule's charge? Add to the chat. Whenever I took this molecule and dumped it into a solution with a pH of 1, it's +2. Now when I add 1 drop of sodium hydroxide, 1 drop's not going to change things radically, but as I continue to add more and more sodium hydroxide, the groups that are protonated, well, some of them begin to be deprotonated. The first one to be deprotonated is the C termini of aspartic acid. It goes from having a 0 charge to a -1 charge, which means my overall molecule goes from a +2 to a +1 charge. Whoever sent that, did that help at all? Okay. Now, this is, like I've said, and I will say again, this is tricky stuff. This is tough stuff, and I think that I shared. Go ahead and pull up the link again. I shared this peptide or this web page. This one that I'm adding to the chat right now. Pepdraw.com. I think that it's fantastic because then you can punch in a molecule's sequence based on its single letter code and get a visual. Okay, what does this look like at a pH of 1? What does it look like at a pH of 7, pH of 9? And it's not going to display the pKa values for you, but it gives you a way to, and I'll actually just go ahead and do one. Are we expected to have the, yes, you are expected to have the amino acid structures memorized by exam 1. Yes. Remember, you have to be able to see them and pick them out. You don't have to be able to draw them. It might be helpful, and that's why it's on your homework, but you just be able to identify them. There's a game on the Apple Store. Fantastic. But here's what we got. ARG. Oh, here we go. ARGYLE. There we go. Argyle. That is a hexapeptide. It has 6 amino acids that make up the peptide. I want to see that molecule at a pH of 1. I'm going to draw this peptide. Now, if you look at the bottom of the screen, that is what this peptide looks like at a pH of 1. I'm going to adjust the pH. I'm going to put it at, let's say 3. What I want you to do is watch closely. But before you do that, I am sharing the screen. Good. I'm going to circle a couple of things on here. Okay. That group is protonated. Protonated. Amino acid quiz is the name of the app, I presume. Let's watch those groups. Okay. When I adjusted my pH up to 7, 2 of those groups got deprotonated. Whenever I go back to 1, my molecule has a charge of +2. Okay, so this molecule, answer in the chat, Y or N. Could this molecule that I've got on the screen at the bottom there, could this ever have a charge of +3? And if you're Asking what to watch or curious what to watch? No, it could not have a charge of +3. Okay, let's see this at a pH of 3. Oh, only the C termini or the C terminal group, which is right here. Only that one got deprotonated. So this is what my molecule looks like at a pH or at a total charge of +1. If we continue increasing, let's go to 6 and take a look at it. Okay, now another group got deprotonated. Let's go to 9 and see what it looks like. Oh, at 9, it still looks the same. 12, 12, I got a charge of -2. Then let's go to 13. Oh, at 13, that's where I get to as extreme as this molecule could possibly be. So this molecule right here has a charge range from +2 all the way to -3. And so if you're thinking like, oh, what are some good, practice problems? Or how could I, what could I do for a practice problem? Punch in words, use your different pKa's, and try to come up with what are the charge possibilities for this molecule. And use this tool right here as kind of an exercise builder for yourself. So this molecule right here could ever have a charge of -4. Every group that's ionizable. So no, you're absolutely right. It could not have a charge of -4. Okay. So I have no problem spending more time on that because that's important stuff. Um, and like I said, if you want to, well, we also need to be able to draw titration curves. You don't need to draw, but you do need to be able to like look at a titration curve and say, you know, what it's possible. Sorry, gotta, um, you might have a question that asks you about a titration curve. And if you're thinking, well, okay, here's the simple way of thinking about a titration curve. If I give you a molecule that has 3 pKa's, your titration curve will have 3 horizontal regions. What I mean by that is your titration curve will look, it's too small. Your titration curve will look like this. Horizontal region, horizontal region, horizontal region. Each one of those corresponds to a pKa. So again, 4 pKa's. There we go. Sorry, that wasn't the cleanest drawing, but 1, 2, 3, and 4. So that's good context for a titration curve. Okay. Now, what we're doing is we're transitioning over into a discussion of protein structure. So what we've worked on primarily is the primary structure of a protein. Primarily, we've worked on primary. The primary structure of a protein is simply the amino acid sequence. So from the N termini to C termini. Anytime you look at a polypeptide that we've drawn or that we've talked about, I'll show you the N terminal amino acid and I'll work through, and there's the C terminal amino acid. So just that sequence is your primary structure. Now, this right here, this is a little bit more complex than that. That has, well, that thing that I've got a big red circle around, those are amino acids. Those are amino acids that build together to make a peptide or a polypeptide. And that polymer of amino acids, well, it has these interesting little folds in it, and it takes on that crazy shape there. Does this right here have a primary structure? Absolutely, because it has amino acids, and the sequence of those amino acids is important. Now, our levels of protein structure range from primary, secondary, tertiary, and quaternary structure. What we want to know and what's important to know about these different levels is that what are the forces that hold them together? We've already talked about covalent bonding. And specifically, we've talked about peptide bonds that hold together the primary structure of a protein. The secondary structure is kind of your next level. These are known as your local structures, and your local structures are commonly known as an alpha helix or a beta sheet. These are held together by backbone hydrogen bonding. Now, this is an important qualification. It's not hydrogen bonding, but backbone hydrogen bonding. And so, what that means is atoms within the backbone of a polypeptide, those are responsible for holding this structure together. Your tertiary structure, well, those are where your R groups interact. So this is where, and one of the important things that we've talked about is, you know, the classification of amino acids. An amino acid like arginine, that can adopt a positive charge. So what do you think arginine will be attracted to? By it having a positive charge, what sort of charge will it be attracted to? Add to the chat. Negative charges. Okay. Now, a little bit next level. What amino acid can you think of that is there that has a negative charge or negatively charged R group? If you could add the single letter code for either of them, that'd be cool. Negatively charged amino acids like aspartic acid and glutamic acid. So if the R groups for aspartic acid and glutamic acid are interacting with one another, what we have going on is R group interactions between different parts of a protein. The quaternary structure of a protein is where multiple proteins fold together. Could you add a 1 in the chat if you've ever heard of the protein hemoglobin, or a 0 in the chat if you have never heard of hemoglobin? Okay. Hemoglobin is an oxygen binding and oxygen carrying protein. It works alongside a protein known as myoglobin to basically help, air from outside make it into all your different tissues so that you can completely oxidize sugars and you can extract energy from them. Now, I bring up hemoglobin, which I will sometimes refer to as HB, because of the fact that hemoglobin is made up of four proteins that kind of fold together. It's four different subunits that kind of fold together to make one protein. Now, we've talked about the primary structure. I feel like a pretty good amount. Typically, I'm going to ask you about the primary structure by looking at the single letter codes. So ARK, I'll ask you, hey, what's this peptide's charge or something like that. But also you could have the three-letter codes. And the three-letter codes follow a capital first letter followed by two lowercase letters. Now, our secondary structure, these are commonly known as your local structures. These are stabilized by backbone hydrogen bonding. So when you think about a peptide, and I'm going to draw a simple peptide down here, NCC, NCC. This says amide hydrogen and carbonyl oxygen will hydrogen bond. Okay, well, let's think about the N termini. And I'll go ahead and make this an R group, and this would be an R sub 1. And R group here I'm using in the context of organic chemistry, where it's just like, oh yeah, this molecule, this polymer goes on. So this nitrogen right here has a hydrogen. And this carbonyl oxygen right here. These two things can hydrogen bond with one another. And so this is what is an example of backbone hydrogen bonding. Now, patterns exist and secondary structures can be predicted. So what that means is that if you know the primary structure, which primary structure is in many times denoted as 1 followed by naught, so it's kind of like 1 degree. That 1 naught indicates primary structure. But if you know the primary structure of a protein, you can predict and guess, does it fold like this? Question mark. Does it make these little local structures? Now, amino acid side chains or R groups can influence if a structure is formed but they are not seen as major contributors to secondary structures. Instead, when it comes to secondary structure formation, the question is really like, well, what is this? Um, what's our distance of these different groups in the backbone? Now, when you think about the secondary structure of a polypeptide, here's our N termini, here's our C termini. It's important to know that what are the groups that can possibly participate in that backbone hydrogen bonding. So this is our amide nitrogen or our hydrogen, and this group right here, these two can potentially pair up. Now, with that in mind, there are some movements of this peptide bond or of a polypeptide like this. And when there are movements, that's going to make, you know, when we think about a molecule, this X right here that I've just drawn, it might be, let's say, from this Y. Is anyone familiar with an angstrom? Add a 1 to the chat if you're familiar with angstroms. Have you ever heard the term? Okay, an angstrom is a measurement. So it's like smaller than a nanometer. Now, X and Y here, this and this, might be 10 angstroms apart. If you think about it in an XY plane or an X plane. Can it hydrogen bond with the carboxyl in the middle? Melanie, you have a great question, and we're going to get there. Are you talking, actually, let me rephrase that. Are you talking about this one right here or this one right here? A or B? Which one are you talking about? Or neither of those? Okay. The one in the middle. Oh, are you talking about this one? Okay. Um, Basically, yes. To answer your question, yes, that can take place. And I'm happy that you're asking about this. I hadn't really thought to mention this, but this right here, that is an R group. That is the R group. That would be glutamic acid. Now, if this were to interact with this, that would be an example of a backbone R group interaction, as opposed to a backbone interaction. Does that make sense? Okay. Okay, great. So when we talk about and sorry, let me rephrase backbone R group interactions, because they relate to the R group, that's going to be reserved for tertiary structure. So that's not a part of the secondary structure. Okay. So when we look at a peptide like what we see on the screen right here, um, you took organic, and in organic chemistry, my memory of organic chemistry was lots of IR spectra, where you would say, okay, well, we've got this bond that this one vibrates and this one does this. Um, so atoms within a molecule, there is some movement. And so this molecule that we're seeing that I'm going to put a box around, that molecule has some fluidity, some movement in it. Would you agree with that? Give me a Y or an N if you agree with that. Okay. Now, with that said, as much as it has movement, it has some limitations to it. One limitation is that this peptide bond right here, and all of these peptide bonds, how are peptide bonds stabilized? Give you a hint. It starts with an R. They're resonance stabilized. When something is resonance stabilized, um, it's not going to have the same properties as as a single bond. It's not going to have the same properties as a secondary bond, sorry, a double bond. Instead, it's kind of in the middle. So it's shorter than a double bond, but or sorry, it's longer than a double bond, but shorter than a single bond. Now, with that in mind, these peptide bonds are very rigid. They don't have a lot of movement. But every other bond on this molecule has some rotation. So what I mean by that is this right here, all of this stuff and all of this stuff, those can move. Those can kind of rotate. Where I have, as opposed to a scribble, I'm going to put an X. Where I have an X, the bonds that are found within those X's, they have some ability to rotate. And what we see is that is how a protein ultimately is going to go from a primary structure and a secondary structure to something that looks like this on the right-hand side. That cool ribbon design. So we have this rotation. Now that rotation and that ability to rotate is something that's been studied. And when those bonds are able to rotate a certain amount, and when they do, they give off a pair of favorable angles. So what I mean by that is, let's say that, okay. Imagine, and if you do this same thing at home. Okay. I've got my hands, palms face down. And if I rotate both of my hands away from me, now I'm looking at my palms. I can rotate them back, rotate, rotate, rotate. Okay. This right here, I'm going to consider to be my 0-degree angle. Okay. Let's say that I get my right hand and I rotate it, and now I'm facing my palm. That has been approximately a 90-degree rotation. Now, I'm not going to ask anyone to say yes or acknowledge that. Now what I'm going to do, I've got my palm facing me with my right palm facing me. Now I'm going to rotate my left hand so that my palm is facing away from me. And if you're anything like me, you can kind of feel a little bit of strain to this. So I'm going back to 0. I'm taking my right palm and I'm rotating it so that I'm looking at my palm. That is a positive 90-degree rotation. Now I'm going to take my left hand and I'm going to rotate that. So now I'm looking at the top of my hand. That is a rotation in the opposite direction. So rather than call that, or what I'm going to call that is a negative 90-degree rotation. So right now, I have my hands that are effectively like bonds that have rotated in 2 different directions. And this rotation, 90 degrees and negative 90, that works for me. It's favorable. It doesn't hurt a whole lot. But if I try to twist my left hand even more, well, now things are getting a little dicey. Because look at got my hands, there we go. The more that I try to rotate my left hand to get more than negative 90 degrees, what happens to my elbow? It begins going up. And the rest of my body moves. Imagine, or what I'm wanting you to visualize is that my arms and my person is basically like this peptide bond. Rotate one angle, rotate another angle. Can I get it to go more? I can, but the entire protein then has to contort itself. Can you give me a 1 in the chat if you participated in that and followed me, or a 0 if you did not do that? If you did not do that, I understand and respect that. That's your call. Okay. Now, what I'm trying to illustrate is that a polypeptide has that same sort of ability. Now, the important thing about this is we have our peptide bond, and here's a zoom in of a peptide bond right here. C to N, that is our peptide bond. N to C is our next bond, and this is known as You could call it the phi or phi, phi angle, or phi bond. So that is the one that follows the peptide bond. The one that precedes the peptide bond is known as your psi angle or psi. Okay, so phi and psi, think about those as being my hands that are rotating. I can rotate one hand 90 degrees and the other one at the same time negative 90. Can I rotate them both 90? Sure. There's a combination of bond angles that I can rotate these and it doesn't hurt. But then there's a combination of bond angles where it's like, that doesn't work. I cannot do that. This plot right here, this is known as a Ramachandran plot. And what this shows me is my favorable combinations of phi and psi angles. Now, when you look at this plot, what this is showing is the shaded regions are the most stable regions. So if I were to adjust a phi angle or a rotation to negative 90 degrees, a negative 90 phi angle, that's going to look right about there on my x-axis. I'm not asking you to remember these like axes as phi or psi, but if I were to adjust the psi angle to, let's say, negative 90, yeah, negative 90. Psi angle to negative 90, we're looking at right about, ooh, there maybe, roughly. So that combination is right about here. This is a rough estimation. So would that produce a favorable angle or would that kind of hurt? That would be an unfavorable bond combination. Can you give me a Y or an N if you follow that? Okay. Can I explain it again? Sure. So what we're looking at is we're just looking at this in terms of is this a favorable or an unfavorable pair? A phi angle of 90 degrees and a psi angle of 120 degrees. Well, I can look at my phi angles labeled on my x-axis and say, okay, positive 90 is right about here. And then positive 120 psi angle is right about there. So if I'm looking at a combination of 90 and 120, that's right about there. That's into the void of whiteness where that is not a favorable combination. Your phi and psi angles of 90 and 120, that's not a favorable combination. What does the blue mean? The blue is the shaded region. That is the region that produces the favorable combination. What makes it favorable? Is it the ability to rotate? It's the ability to reach that rotation. So is the top left quadrant where the favorable combinations occur? Yes, it is. So if you look at this map, really there aren't many favorable combinations. It's a very small fraction of them. Now, this is important because what this says is if you, let's say hypothetically that we got a peptide and we rotated the phi angle to be 90 and the psi angle to be 120, what's going to probably happen? Well, it's going to be unstable. It's not going to be able to hold that position. And instead, it's going to kind of unwind really abruptly. And if it does hold that, well, it's going to be unstable. Can you give me a 1 or a 0? 1 if you follow, a 0 if you don't. Okay, I got a private message. Is the blue region in the bottom quadrant also considered a favorable combination or is it not favorable? The blue and all of the blue regions, whether they're light blue or darker blue, they are considered favorable. Some of them, like the in the upper left-hand side, like this region right here is has more favorable combinations than this region outside of that. Okay. So, yeah, does this chart apply to all phi and psi angles? Ooh, great question, Melanie. Yes, it does. So this is, let me clarify, this is pretty much an average. Um, is there some wiggle room? Is there some slight variation? Yeah, a little bit, but this is a pretty good reflection of you've randomly generated a peptide. What are the favorable or what are the combinations? It's going to look like this. Are there some where you can like fine tune it to make a peptide that's leucine, isoleucine, leucine, 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 alanine, and you can get some other combination? Yeah, but this is a pretty good average. Melanie, that's a great question. That's a very insightful question. Okay. Now this is important for understanding the connection between primary structure and secondary structures. Now, our first secondary structure is known as an alpha helix. This is maybe the secondary structure that people are most familiar with. It's stabilized by hydrogen bonds between the amide nitrogen and carbonyl oxygen. This is considered a right-handed helix. If you ever have talked about a DNA double strand or a DS double dsDNA or a double-stranded DNA molecule, DNA is considered a left-handed helix. Now, the difference between those handedness is it all comes back to if your thumb is going in the center of that helix, the directionality that is going to rotate upwards follows your palm or follows your fingers as they fold in. So it's a right-handed helix whenever it goes up. I guess if you're looking up it would be that way. A left-handed helix is going to go in the opposite direction. An alpha helix is a right-handed helix. If there's a takeaway from this, that would be it, that it's a right-handed helix. Now, this is a cylinder shape. Different parts of the helix are above one another. If you've ever been on a spiral staircase, that's the most helpful thing for me when it comes to visualizing this. You're on a spiral staircase. Now, the height of one complete rotation is 5.4 angstroms. Each amino acid is approximately 1.5 angstroms in all directions. So what that means is going in the basically this is not in an XY plane, it's an X, Y, and Z plane. So each amino acid spans this region, but also kind of up and back. Now, one complete rotation requires approximately 3.6 amino acids. Now, could you give me, well, actually, I want you to think about this spiral staircase. If you need a little bit of a support in thinking about this, the way that I visualize it is, let's say that me and my friend are walking up a spiral staircase. When my friend is standing, like my friend's gone up the spiral staircase, I start at the very bottom of it. I look up and my friend is standing right above me. And I say, hey, there's your shoes. From my feet to their feet is 5.4 angstroms. So that's the distance, 5.4 angstroms. Now, if you were to imagine, okay, well, how do I get from my first position to their position? That would be approximately 3.6 amino acids. Now, this right here is bringing up our first instance of some alpha helix related math. So here's the sort of question that I want you to be able to answer. Let's say that you have an alpha helix with, let's say, 8 rotations, 8 full rotations. So again, you could think about this as like a spiral staircase. Well, there are 8 complete rotations. So that means you could stand at the bottom, another friend above you, and so on and so on and so on. How tall is that alpha helix? Well, 8 full rotations. Each rotation is 5.4 angstroms. So we're talking about 8 times 5.4, which would be approximately 43.2. How about 43, not 403, Joel? 43.2. Does everyone follow my math there? Okay. Now, another follow-up question for that would be, well, how many amino acids would be required for that? Well, then you're going to say 8 times 3.6. Because if it's 3.6 amino acids per complete rotation, then we're talking about 26.4, I think, approximately. Because one rotation is 3.6, two rotations is 7.2, three rotations is 10.8. I could go on flexing my math ability with my addition of 3.6, but could I get a 1 in the chat if you follow the math and a 2 of I'm a little bit perplexed by that. A Y also works. Okay, cool. So these are questions that I want you to be able to answer. How tall is a helix? How many amino acids are required for that helix? And to work those questions backwards. You have an alpha helix that's 64.2 angstroms. How many rotations? How many amino acids? You have an alpha helix composed of 112 amino acids. How tall is that? How many rotations? So that same question, just deconstruct it and reassemble it in slightly different ways. Now, the average alpha helix has approximately 10 amino acids. Does that mean that every alpha helix has 10 amino acids? Nope. Just the average alpha helix has 10 amino acids. Ooh, will I ask about half rotations too? Unlikely. Unlikely. And if I did, I would, you're going to have multiple choice, multiple select answers. So your questions would kind of, your answer options would not be like, oh, but if I round it this way or if I round it that way. So I think you're going to be in good shape there. Now, one of the things that I've noticed over the years that people get mixed up on is they take this prompt or that stem. Average alpha helix has 10 amino acids. Okay. And then if I say, how many rotations? Does the average alpha helix have? Well, that's kind of a tricky question, and it can be asked in a tricky way. If the question is like, how many complete rotations? Well, complete rotations would be two. If I don't ask about complete rotations, which I'm not intending to ask this sort of tricky question, it would be something like 2.7. Now, after that, what I've noticed people have a tendency to do is they say, okay, well, how many rotations, how many amino acids, how tall is this? Well, 10 amino acids. Okay. Each amino acid, each AA is 1.5 angstroms. Well, each amino acid is 1.5, so 10 times 1.5 would mean approximately 15 angstroms. That's how tall this is. Okay. Now, your carbonyl oxygen is going to be hydrogen bonded to the NH of the fourth amino acid away. This follows an I to an I plus 4 pattern. So I being our first amino acid, and then, well, whatever number that is. What I mean by this is an alpha helix doesn't necessarily start at amino acid number 1 on a polypeptide. You could have a polypeptide that's 375 amino acids long. Well, if you have this amino acid, it's going to hydrogen bond with one that is 4 away. In which case, this could be like 366, and this would be 370 because this is our I to I plus 4. Okay. Now, what that also means is when we have hydrogen bonding, this amino acid hydrogen bonds with this amino acid. The next amino acid hydrogen bonds with the next one. So when you talk about an alpha helix, it's not just one hydrogen bond that forms. It's multiple. Okay. It is 1:50 p.m. I'm going to stop right here. Anyone's welcome to hang around and ask questions if they want. I'm going to stop my recording.